In this first video of Introduction to Mathematical Thinking, we're going to define what a set is, and in the next video, you'll define some basic set operations before we start to talk about what a function is in terms of set theory. So let's get started. So first, let's define what a set is. And in mathematics, we say a set is a well-defined collection of objects. And by well-defined, we mean that for any object x, and now x could be a number, but it doesn't have to be, right? X could be anything. A vector, a matrix, x could even represent a student in this course, right? But by well-defined, we mean that for any object x, we can easily determine whether or not x is an element or a member of the set. So for example, the set of students in this class is well-defined because we can easily check if any student in Berkeley is in this class. I just look and see, are they in lecture? Okay? To write this in mathematical notation, if x is a member, or x is any element, and S is a set, the way we write x is part of the set is with this notation. This means element of. If we want to say the opposite, that x is not an element of the set, we would write the same thing, but cross out the element of. So this means not an element of. Okay, so for example, if we let S be the set 1, 2, 3, 4, 2 is an element of S, but 5 is not an element of S. So that's how we define a set. So in terms of actually listing out or defining what elements are in a set, we can do this two ways. One is by listing out what all the elements in the set are. So for example, in A1, we have a collection of four numbers, 1, 3.14, negative 15, and pi plus e. In A2, we have the set of all integers, and with the dots on either side, we can sort of infer what the other numbers in the pattern are. And in A3, we have a collection of 3 basketball players. And one thing to note is that sets are not inherently ordered, right? So in either A1 or A3, I could reverse the order of any of these elements and it would be the same set. In A2, I could also change the order up, but it sort of makes more sense to write it in this way so that we can infer what comes to the left of negative 3 and to the right of 2. Okay, so that's one way we can define a set. The other way we can define a set is by stating a property that identifies whether or not an element is in the set. And this is called set builder notation. A4 is the set of all x's such that x plus 3 is prime. So it'll go through, find all prime numbers, subtract 3 from them, and add them to the set. A5 is the set of all numbers such that that number squared minus 5 times that number plus 6 is equal to 0. Okay, so this is how we specify what elements are in a set. And this colon here means such that. And we can also replace this colon with a vertical bar. So another way we could define A5 is by writing t vertical bar, t squared minus 5t plus 6 is equal to 0. So what this should remind you of in terms of programming is list comprehensions, right? So for example, if I want the set, I don't know, x squared, such that x is between 0 and 10, and x is an integer, and we'll talk more about what an integer is formally in a few lectures from now. But if we want this set, we could also do this in Python as a list comprehension, where we have x squared for x in range 11. So these two things mean the same thing, right? This is just called set builder notation. This is called list comprehension. So that's how we can define a set. One measure we need to define is what the size of a set is. And for now, we're going to restrict this to be about sets of finitely many elements. So we'll talk more about infinitely large sets and how we can determine what their size is in a few lectures from now. But for now, let's stick with finite sets. So we say the cardinality of a set with finitely many elements is the number of elements in it, and it's represented by these vertical bars, okay? So let's say A is some set 1, 2, 4, 5, 7. We say the cardinality of A is 5, okay? And two things. One, sets are not ordered, and two, sets do not count duplicates, okay? So if I have this set B, which contains the same elements, but with some of them duplicated, the cardinality of B is also 5, okay? So all we care about is unique elements, and we do not care about ordering, okay? So that's our definition of the size of a set, or the cardinality, for now. Now let's define what a subset is, okay? So given some set A, we say another set B is a subset of A if and only if. So this means this condition goes both ways. We'll talk more about this when we get to propositional logic. But B is a subset of A if and only if every element in B is also an element of A. And equivalently, we can say A is a superset of B. Okay, let's get some notation down. So to say B is a subset of A, we can write this. B subset A. Okay? Or equivalently, we can write A is a superset of B. And don't confuse this notation with less than or greater than signs. Okay? Even though they do look very similar. They're more of rounded C's. Okay? So this means B is a subset of A, or A is a superset of B. But this allows for B and A to be equal, just like the difference between X is greater than or equal to Y versus X is greater than Y. This is the one without the bar underneath is strict. So X cannot be equal to Y. So these are called subsets / supersets. Usually we don't really use this second notation. We prefer to use the first one. But we also have this idea of a proper subset. And that is a subset where equality is not allowed. So if we write B is a proper subset of A, notice the bar underneath is not there. This means B is a subset of A and not equal to A. Okay? So what this means, on the right side, B contains some number of elements from A, but not all of them. Okay? And on the left side, it also means the same thing. B contains some number of elements from A. It could also contain all elements in A. Okay? So here, equality is allowed. Cool. So now we know what subsets and supersets are.